Dear colleagues, our today's report is devoted to a thin-walled pipe exposed to corrosion under pressure and non-uniform heating. The outline of presentation looks like this. Corrosion causes irreparable damages of industrial and building structures and leads to reduction of their durability. According to open data, the annual corrosion costs ranged from 3 to 6% of the gross national product of each nation. There are a lot of classifications of types of corrosion. On the screen you can see only some of them. We will consider a surface general corrosion and more specifically mechanochemical corrosion. Originally, the term mechanochemical corrosion was introduced by Immanuel Gutmann with respect to general corrosion facilitated by mechanical stress, to be more precise, for anodic dissolution of deformed metals. So, mechanochemical corrosion is more intensive than the simple superposition of damages induced by mechanical stresses and electrochemical corrosion taken separately. There exist various models of corrosion kinetics. Gutmann received the exponential dependence of the corrosion rate on the mechanical stress. According to Rusanov, dissolution rate is a quadratic function of strain components. According to experimental results, the rate of general corrosion is often a linear function of stress, if stress increases beyond a given threshold. This model with zero thresholds will be used in our work. Consider a linearly elastic thin-walled pipe exposed to corrosion under internal and external pressures of different environments at generally different temperatures. Let the inner and outer radii of the pipe be denoted by small and large r respectively. Assume that the corrosion process is uniform along inside and outside surfaces with the rates denoted by Vr. We will consider only those situations when the maximal stress used in the corrosion kinetics equations is the Hoops stress. First, let's take a look at the known solution of the problem based on the classical thin shell model. In such case, maximum stress is expressed by the Navier's formula and assumed to be constant through shell's thickness. The problem is reduced to ordinary differential equation in the thickness of the shell. As we can see, this solution does not reflect the effect of internal and external pressure values themselves, but depends only on their difference. Explicit solution of the thermal elasticity problem for the pipe under internal and external pressures and different temperatures is known. Solution to the corrosion problem based on Lamès and Lorenz's formulas is rather cumbersome. Here you can see it only for the one-sided corrosion, so we tried to simplify it. After certain transformations, Lamès and Lorenz's equations can be simplified to the following form, which differs from the classical thin shell solution by the constant terms. Substituting the both expressions for the stresses in the corrosion kinetics equations, we obtain the equation for the evolution of the pipe thickness with time. Solution of this differential equation can be obtained in this simple form, which is absolutely the same as the solution based on the classical thin shell theory, with only constants a and m being different. Let us compare all the solutions discussed when applied to relatively thin shells. This graph shows the dependencies of the absolute values of the maximal Hoops stress on time during the corrosion process for various sets of internal and external pressures, so that the absolute value of their difference remains constant, the temperatures inside and outside being equal. Note that at equal temperatures, maximal Hoops stress is always at the internal surface of the pipe. The solution based on the classical thin shell model gives only one curve, the black solid line on the figure. At the same time, the accurate solution based on the Lamé formulas and our new solution reflect the effect of hydrostatic pressure and demonstrate a perfect coincidence of the results. Here and below we use megapascal as units of stress and pressures. The rate of corrosion is measured in millimeters per year. Using the thin shell model for the problems of mechanochemical corrosion can lead to a significant error when both internal and external pressures are high enough. As we can see from the table, the greater both pressures are, the more the error grows. So, the solution based on the thin shell theory can give essentially overestimated lifetime for large pressures that can lead to dangerous situations. If we define lifetime of the tube as the time when stress reaches a given strength limit, then we can see that for positive pressure difference, the thin shell model gives underestimated lifetime, while for negative overestimated. For comparison, this slide shows the results for simple corrosion, which is not accelerated by stress, for various sets of pressures when the absolute value of their difference remains constant. In such cases, all the curves tend to one vertical asymptote. So, for pure corrosive wear, when initial stresses are relatively small, there is almost no any difference in the results concerning to the models involved. However, as we can see from the second plot, when the initial stresses are high enough compared to their limiting value, the difference in the lifetimes can be essential. From this slide, we can see that depending on the relationship between the pressures and the temperature difference, hoop stress can reach its maximum in absolute value, either at the internal or at the external surface. In the first case, on the left plot, the maximal hoop stress is at the internal surface, and in the second case, on the right plot, is at the external surface. The growth of the maximal stress determines the life of the pipe in each case. The change in the location of the maximal hoop stress may affect a little the life of the pipe. These figures demonstrate the effect of the difference between the temperatures on the internal and external surfaces at the fixed pressures. As we can see, the difference between the internal and external temperatures has a less effect on the lifetime than the pressure difference at relatively small initial stresses. However, note that the temperatures can directly change the constant part of the corrosion rate, affecting their life even at the equal temperatures inside and outside, i.e. at zero thermal stresses. To analyze the role of the elastic and thermal stress components, we build the graphs of their growth with time taken separately during the process of the shell thinning. It is observed that the elastic stresses, blue solid and dashed lines for external and internal boundaries respectively, increase significantly during the dissolution of the shell, while the thermal stresses, red solid and dashed lines, practically do not change with time. Note that in the framework of thin shell model, the change in the thermal stresses with time is neglected at all. Therefore, that is the elastic stress component which takes part in the mechanochemical effect and leads to synergetic growth of total stress and the rate of dissolution, but not the thermal stress. Using the classical thin shell model can lead to a large error in the lifetime of the pipe subjected to mechanochemical corrosion under pressure and non-uniform heating at large pressures, especially when their common part is greater than their difference. We obtained a new solution that has a simple form, absolutely the same as the solution based on the classical thin shell model, only the constants of the model being different. However, this little change makes our model almost as accurate as the cumbersome exact solution. Our analysis revealed that the elastic, but not the thermal, stress component plays a decisive role in the synergistic growth of the total stress and the corrosion rate. The life of the pipe is determined by the competition of the following processes: the change in the thermo-elastic stresses at the pipe surfaces, the change in the constant path of the corrosion rates due to temperatures, and the possible reversal in the location of the maximal hoop stress from the inner to the outer surface if the signs of the elastic and thermal stress components on the inner surface are opposite. Here is the list of several references. Thank you very much for your attention.